All right, well, welcome to my talk, and thanks for coming. I hope you've enjoyed the conference so far. Title of my talk is Algorithm Intuition, and let's just jump into it. So the first thing I want to say is I'm not an expert, I'm just a dude. This is a quote from Scott Scher, who gave a talk in CPPCon 2015, and he said the following.
If you have an answer for me, because I'm not an expert, I'm just a dude, if you have an answer for me, or if you have questions or whatever else, not only do you get to ask your question or make your statement, but you also get chocolate.
So I stole the quote, and I also stole the gimmick. So our volunteer here has chocolates. Hopefully he can throw them out if you guys have questions. I'll try and throw that thing to you, just so that I don't slow myself down trying to throw you guys chocolates. And then also, I don't have to be held guilty if he hit someone in the head like Bryce did last night. So first things first, a little bit about me. This should be like C++ facts about me. I love C++. I've been coding in C++ for 5 years. There's an asterisk next to it because for the first 3, I wasn't using any algorithms or any data structures from the STL libraries. So really, everything I've learned has been in the last 2 years. I love auto. I'm definitely in the AAA camp, almost always auto. I prefer east const, and I've actually hidden 1 const west in all of my slides. 2 chocolates to the person who can find it. I prefer east-end functions. So those of you who are not familiar, last year Phil Nash gave a talk called, or a lightning talk called "We Have Always Been at War with West Constia," and he was arguing for trailing return types, which he termed east-end functions. And one of the motivations he gave was that a number of other languages do it. So Swift does it, Haskell does it, and he also says that mathematics notation commonly does it as well. I thought this was going to be followed by a number of other slides with other languages, but it wasn't. He stopped at 2 languages, so I'm going to enhance that. Rust has trailing return type. Python 3 with type annotations has trailing return type. Go has trailing return type. Kotlin has trailing return type. If this isn't enough reasons to do trailing return type, and those of you not familiar with the syntax, it's using auto, where you would typically put your explicit return type and then trailing return type at the end. So I'm definitely all for east-end functions. It lets me write Haskell or code, C++ code that looks like Haskell. And also, for those of you who are at C++ Lightning Talks last night, Chandler gave a Lightning Challenge where he showed a minimal and clean API for a map. And if for those of you that noticed, he was using trailing return types. And it enabled the autos all lining up and each of his 4 methods lining up, which in my opinion looks really, really nice. So if you don't believe me, believe Chandler. So back to this. I love algorithms, especially STL algorithms. That's what we're going to be talking about today. And I'm very interested in programming languages in general, not just C++, although C++ is my favorite at the moment. And I like to compete in competitive programming contests. So for those of you that listen to CPPcast, I was on episode 139 if you want to hear more about competitive coding. And throughout this talk, there's going to be 3 or 4 examples that are pulled from these competitive programming websites to motivate when you should use different types of STL algorithms. So let's go back in time to the beginning. The year is 2013. The conference is going native. The speaker is Sean Parent, and the talk is C++ seasoning.
That's a rotate.
So anyone in the room, were they there for this talk? No hands? Who has seen this talk and knows this quote? That's surprising, about half the room. So Sean gave this seminal talk, which is probably one of the most well-known C++ talks to date, and he advocates for algorithms. He says that's a rotate, and he also says it 24 more times.
That's a rotate. That's a rotate. That's a rotate. That's rotate. The rotate. Rotate. A rotate, because rotate, rotate, rotate with rotate. Rotate, 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 and rotate, rotate, and rotate, 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 and a rotate. Rotate is a very common operation. That's a rotate.
So clearly, Sean Parent is a big fan of rotate. But also in the talk, he mentions a plethora of other algorithms.
That's a find if. Find if, the find if, lower bound, 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 lower bound. It's called stable partition. Stable partition, the stable partition. Stable partition, stable partitions, stable partition. Stable partition, stable sort. Stable sort does that. Nth element, nth element, nth element, nth element. That's a rotate.
So if you haven't seen this talk, I basically just summarized it, but you should go back and watch it. It's a fantastic talk. But the most important thing that he says in his whole talk is the following, in my opinion.
So you have all these algorithms at your disposal, right? Learn them. It's very important.
So this was back in 2013, and this led to what I would call a new age in C++, and if not a new age, then at least a trend of other speakers referring back to this talk in their talks about how you should know your algorithms. The next is CPPCon 2016, when Marshall Cloud gave a talk about STL algorithms and how you should use them and write your own.
One of the things that various people have talked about in the last several years is using standard algorithms as in your code.
Moving on to 2017, meeting C++, Kate Gregory.
Simplicity is not just for beginners. To really write simple code, you need to know so much. You need to know the language. You need to know the whole language. You need to know the patterns and the idioms that we use. You need to know the libraries. Sean's implementation of things where he says this is obviously a rotate and all I need to do is a partition followed by a blah blah, he ends up with like really simple code because he knows the algorithms. That's not, again, a paradox or an oddity. That's actually the secret sauce.
And then a few months later, at ACCU 2018, Kate Gregory again.
So I mentioned the ranged 4. You find a loop that touches every element in the collection. Maybe I should change it to a ranged 4. Or better still, maybe I should go look in algorithm. If you've seen the Sean Parent talk, where he first starts talking about algorithm, and he says, hilariously, this is obviously a rotate. And I was in a room full of really smart people, as we are today, and I'm looking around like, they don't think it's obvious, do they? It's not just me, is it? It was not obviously a rotate. But you want to get there. You want to be able to say, hey, this is obviously a rotate.
And at the same conference, ACCU 2018, John Picara gave a very popular talk by the title 105 STL Algorithms in an Hour.
So there's a fact that's been popularized across the C++ community over the past couple of years, is that we need to know all the STL algorithms. We've already seen that talk from Sean Parent a couple of years ago, who transformed a big chunk of code into a very small and expressive piece of code just by choosing the algorithms correctly.
And finally, a few months later, at Code Dive, Odin Holmes
says, hey, that's an accumulate. I know what that does. Who knows what that does? Good crowd, most of you. Learn your algorithms, learn your patterns.
And then a quote from a CPPcast episode, which gave me the title of my talk.
Sort of a Sean moment. If you watched his seasoning talk where he says, well, this is obviously a rotate, and the whole audience goes, huh? What? That moment where someone says, well, it's pretty obvious we can use upper bound for this, and, does it in a single line. And you have a moment of going, what? And then, yeah, sure, right. That is what upper bound can do for us. Absolutely. Got it. I knew that. Totally. I was going to type that myself, but you did it first. And we all have to start going through this, that, I think in about 5 years, C++ developers who don't recognize opportunities for rotate and upper bound and really all of algorithm are going to be kind of in the dust compared to the people who spot something in the real world. And just as you can say, that would be a good use of a linked list, we don't have that intuition about algorithms yet, and we need to.
Anybody know who that was? Kate Gregory, episode 30. I definitely go listen to it. We don't have that intuition about algorithms yet, and we need to. When I heard this line, I knew that was what I was going to call this talk. That was about a year ago. So thank you, Kate. I'm sorry for stealing your words, but it's an awesome title talk. So we're going to bring it full circle back to Sean Parent, who gave a talk at Pacific C++ called Generic Programming, where he said the following.
One of the main algorithms inside of STL is stable sort, and it's an in situ stable sort. And not that long before the STL was published in Knuth's Art of Computer Programming, an in situ stable sort that was solvable in polylog n time was rated as an open exercise, meaning that there was no known solution, right? And Alex has this beautiful little solution in there for stable sort that builds it up out of all the other algorithms. All the algorithms within the STL fit together like puzzle pieces, right? I saw this and I thought, who writes code like this? Okay, right? I mean, keep in mind here, I'm working with a bunch of phenomenal engineers, right? Great people. These are some of the top people in the industry. And I've never seen somebody who writes code like this. Okay? This is not like the code that Alex published in his paper 5 years before, right? He's clearly grown and had some time to think about it. So it's just this phenomenal piece of work. And for me, it was like I want to write code like that. How do I write code like that?
It's this phenomenal piece of work, and for me, it was like, I want to write code like that. This is someone who inspires me, talking about Alex Stepanov, someone who inspires him. For me, this is awesome. Just listening to all these talks and then hearing Sean say this a few months ago, it's what motivated this talk, or contributed to motivating this talk. So I want to develop algorithm tuition, I want to write phenomenal code, and I want to write beautiful code. The last quote is actually from one of my favorite television shows, Black Mirror.
The procedural algorithm is amazing. It's just some beautiful code.
Thank you.
Beautiful code. Beautiful code.
One more time.
Beautiful code.
We live in a golden age of television where a software developer can watch a television show of other software developers telling them how beautiful their code is. This is like my career goal. I just want my colleagues to come up to me and say, that is some
Beautiful code.
Anyways, so that's what motivated this talk, and the goal for today for you is hopefully to get you excited about algorithms. Hopefully I've already done that a little bit. To learn a new algorithm, I know everyone in this room is an expert, so potentially you won't learn a new algorithm, but maybe you'll start to develop some algorithm intuition about how you can make use of some of these algorithms. So we're going to start with a warm-up question. Not that any of the experts in this room need a warm-up question, but maybe some of the people watching this on YouTube later will. And so the question is, given an array of integers, find the difference between the minimum and the maximum. So we're going to go through sort of the worst response to this question, to the best response. And this isn't supposed to be a trick question. This isn't supposed to show how clever you are to solve it. It's just supposed to go through, show a number of different ways and how we can use sort of more modern C++ features to get to the best solution. So we're going to whip through this because I've got other content to get to. So the first solution, quadratic and time complexity. It's basically just setting a local variable answer to the minimum possible value an integer can assume, and then in the nested for loop, 2 indexes i and j, and just resetting that variable to be the maximum difference that you see so far. Note that on the first line, we're using C++17's CTAD, class template argument deduction. But who likes this solution? For the record, no hands went up. So we can slightly improve this solution without reducing the time complexity by using a C++11 feature. Anybody know what it is? Range 4. So doesn't make it look that much better, but it is an improvement. So just note, whenever you're accessing every single element in a range and you don't need the index, use a range-based for loop. Moving on to the next solution, slightly better time complexity, n log n. The solution here is to sort the elements and then subtract the last one from the first one, because we know in a sorted list, the last one's going to be the largest, and the first one's going to be the smallest. It's not that good, though, because at the end, we're dereferencing decremented iterator, which is returned to us by end, and then dereferencing begin. So we can slightly improve this by dereferencing our begin, which is a reverse iterator that gives us basically the first element at the end of the list. But there's a way that we can improve this even more without having to dereference. Does anybody know? Someone said it. Throw him a chocolate, and also throw Ben a chocolate. So yes, not only should you know your algorithms, you should know the methods on your data structures. Next solution. So now we're at optimal time complexity. This is linear. We basically have 2 locals, A and B, that are going to be our minimum and maximum, range-based for loop going through, resetting them. However, we can use 2 STL algorithms to solve this, min element and max element. So some would argue this is less efficient because now we have 2 for loops, so we're going to be incrementing our index more than we need to. But this is just to illustrate that we have 2 algorithms that we can use to solve this. So who knows an algorithm better than these 2 that we can use to solve this problem? Min-max element. All right, just throw everyone a chocolate. So yes. Oh yes, and C++20 will have our range-based versions of these algorithms, so we don't have to pass the iterators. Yeah, just throw one to everyone. I got a second bag here that I can give to you. So as everyone mentioned, Min-max element is an algorithm that we can use that returns a pair of both the minimum and the maximum from our list. So here we're storing a p, which is a pair, and then just subtracting p dot first from p dot second after dereferencing them because they're iterators. Anyone know a C++17 structure binding? Store one to Vittorio. Thank you. So structure bindings, probably one of my favorite C++17 features. I know it's just syntax sugar, but for me, it's amazing. It enables you to name and destructure the first and second from your pair. And so then we can just dereference B minus dereference A. And with C++20, we'll have the range-based version of this algorithm, and we won't need to pass the iterators. So this makes me extremely happy. On the first line, we're using C++17 CTAD. The second line, C++17 structure bindings. We're making use of what I thought was a more esoteric algorithm, min-max element, but apparently everyone in the room knows it. And then we're just returning the difference. So not a very complicated example, but it illustrates a number of different features you can use. And I think this code is beautiful. There are a few things wrong. Oh, Ben?
I was going to say, something you didn't mention, min-max element isn't just a syntactic nicety of one.
Right. It does it. Yes, it does in fewer comparisons, and it's one loop. So it is more efficient. Same time complexity as the previous solution, but it is actually a more efficient solution. So there's a few things wrong with the solution that I'm sure a few of you are thinking, it's not that beautiful. So I just want to point them out and make a point that this is just slideware. So slideware disclaimer. The number one mistake that I'm making here is I'm not using std namespace. I don't use std namespace on most of my slides unless if I'm referring to a function object in one of the function headers, just because I think it makes it look cleaner. Solve, terrible function name. A and B, terrible variable names. Name your functions better, name your variables better in production code. And sort of failing solid, so the D in solid, obviously everyone knows, is dependency inversion. Typically this refers more to classes, but the fact that I'm hard coding my vector into my function shouldn't be doing that. It should be a generic function that I can call over and over again. But the point is, if you're noticing small things like this in my code, know that I'm aware of them too, and that this is just slideware code. All right, a small digression. We're going to take a look at one of the previous examples, which is this one here. And there's a small improvement we can make to this. And when I initially wrote these slides, I didn't have this in any of my slides. And it was only because of listening to a podcast that I ended up discovering this. So the point that I'm going to make here is that everyone should go read this book. Who has read this book? Raise your hands. One person. So everyone should go read it. It's edited by Kevlin Henney. 97 Things Every Programmer Should Know. It's just a collection of points. One of the points is continuous learning. And in one of those subpoints, it says, follow the advice of the pragmatic programmers. And if we go there, take a look at what it says in chapter 1, basically says the same thing, but it's learn at least one new language every year. Different languages solve the same problems in different ways. By learning several different approaches, you can help broaden your thinking. And I can't agree with this more. I've been learning Haskell recently. It's changing the way that I write C++ code. How does this get us back to this? Well, when I was listening to this podcast, Functional Geekery, amazing podcast for those of you interested in functional programming, they made a comment about Ruby, and also JavaScript, but mainly the point was about Ruby. And it's that they have this syntax of an exclamation mark that notates a mutating method. So you'll have a piece of code like this, s is equal to string, and then you call strip, which is a mutating method, and that's what the exclamation mark denotes. It notes that you're modifying the underlying data structure. And another digression inside this digression is that exclamation marks mean different things in different languages. So in Ruby, it's a mutating method. Rust, it's a macro, not C style, Lisp style. D, it's a template type, similar to the angle brackets in C++. And Haskell, it means strictness. So don't think that exclamation mark means this in every language. The point is, every language has their own opinion. End of the inner digression, and back to the first digression. So how can we modify min-max elements that isn't mutating the underlying data structure, but technically it could be? What change can we make? Does anybody know? Vittorio gets another chocolate. The C. So I've seen in many presentations that talk about algorithms, and not most of them don't have this. It's a small change that I think shouldn't be excluded from slideware that makes a huge difference. If you like functional programming, this is much more functional. And if you're going to take one thing away from my talk, this is like number 4 out of 10. So I think this is an important point. Know that when you're using algorithms, you should think, am I mutating? If I'm not, use the const versions of these. So that's the end of that digression. These are some different solutions just because it's fun. Python is always the most terse. Java, don't really like Java. And then Haskell. So moving on to the bulk of the content of my talk. We're going to start by stealing some content from Jonathan Bakar's talk, the 105 STL algorithms. So, going to plug him a bit. Go watch this talk because I'm about to steal his content. He gave it both at ACCU and at CPPCon. And he's got a great blog, Fluent C++, which I'm sure many of you are familiar with. So he shows this map called the world of C++ STL algorithms. And on it, he sort of combines all the algorithms into different regions based on sort of properties. So the first comment I'm going to make on this map is that there are not 105 algorithms on this map. There's 71, because I counted. Part of this is because of the fact that in the bottom left corner, he's got this secret rune section. And the secret runes are basically the prefixes and the suffixes that you can append to algorithms to get slightly different ones. So we heard Sean Parent say earlier, stable partition, stable sort. That's using the stable prefix added to sort and partition, which are also algorithms. So he only shows the partition and the sort algorithms, and he sort of says you can combine the secret runes to get more. So if we add those, we get 32 algorithms that aren't shown on the map, which gives us 103. Still too short of 105. So I went and checked, and these are the 8 that he left out. And of course, I then went and tweeted at him, Jonathan, what are the 2 that get us to 105? And he responded, find if not is indeed counted, as it's in the slides, not the others you're mentioning, because they don't take a begin and end. So that still only gets us to 104. I don't think we'll ever know what the missing 105th algorithm is. But at least we know that the motivation, so yeah, find if not is the one that was included. The rest of these don't take a begin and end. So yeah, we'll never know. But the point to know is that what motivated the algorithms going on this slide are the ones that take iterators. The second point that I want to make is that Jonathan left off, I think, a crucial island or isle on this map. So it's a secret isle, so maybe that's why he left it off, but I decided to add it. And it's the lost isle of operators, just down at the bottom here. And so what these are is these are function objects that the function header provides us with. When I starting to use algorithms more, I was constantly writing lambdas that just took 2 parameters, a and b, and then just added them or multiplied them. We already have these. They're in the function header. If you find yourself writing simple lambdas over and over again that just sort of wrap an operator, use the function objects that are in the function header. And obviously, or not obviously, they're called operator wrappers for that fact, because basically they're just wrapping an operator. So on to our algorithms. It isn't explicitly stated in his talk, but there are 3 different headers that are included on that map: algorithm, numeric, and memory. And this is the breakdown across the different C++ versions. So pre-C++ 11, C++ 11, and C++ 17. So in total, there's actually 111, the 104 plus the 7 that he left off. And anyone know the one algorithm that we deleted in C++ 17? Ben gets another chocolate. Better watch out. You need to go on a diet, Ben. Oh, he doesn't want the chocolate. Anyway, so we're going to focus mostly on the numeric algorithms in this talk. So does anyone know one of the 4 original numeric algorithms? Ben. Iota. That's actually incorrect. Bryce. Accumulate. Throw him a chocolate. That's 1. What? OK, 4 chocolates to Bryce. Yeah. Yeah. Partial sum. Those are the 4. 4 chocolates to Bryce. And we'll ask Ben. Oh, you're talking about, so for the people online, Ben was talking about APL, not C++. That's why he got confused. APL, for those of you that don't know, stands for A Programming Language. And it's got a beautiful syntax. Anyone know the C++ 11 algorithm, Ben? Iota. So these are them. In blue are the pre-C++ 11. In yellow is the ones C++ 11. And then in green are the C++ 17. So we're quickly going to look at Iota. There's not much algorithm intuition to be developed here. You just need to know about it. It basically, given a range, generates a sequence. If you give it forward iterators, it goes 1 to 10. If you give it reverse iterators, it goes backwards. I had more to say about this, but I don't have time in this talk. Maybe I'll give it in a lightning talk in the future. If you want, go and search on Twitter for Iota shaming. There was a Twitter storm that happened back in January, but I'm not going to talk more about it here. But it is entertaining. So Iota, check. Next algorithm we're going to talk about is accumulate. So this is another slide stolen from Jonathan's talks. And in this, he shows basically visually what the default operations of each of these algorithms are. So first, we're going to look at accumulate. You can see here each of these pluses. So the default binary operation that accumulate comes with is plus. And we're going to sort of burn through this next part because I'm sure, who's familiar with accumulate? Raise a hands. Actually, less than I would expect. I'd say 80% of the room put up their hand. So accumulate. You pass it 2 iterators, an initial value, and it's just going to sum the elements. It's going to add them. So we're going to get 6, 1 plus 2 plus 3. This is the exact same as this. This is the default binary operation or function object that accumulate comes with. But we can override it. So we can pass it multiplies. We want to change the identity value because if we have an identity value of 0, you're going to end up with 0. But this isn't really that nice because for me, accumulate has the semantic value of sort of adding things. You know, you accumulate wealth, you accumulate a number of other things, and it's sort of adding this stuff up. You're not necessarily multiplicatively performing an operation on it. So it's not the best name. Enter C++17's reduce. Basically the same algorithm. There are a few differences, but for this example, they do the same thing. So the first line, and note that you can actually drop your identity value if you're using the default binary operation plus, and it'll just default it to 0. So that's sort of nice. The second line where we're setting y does the exact same thing, and then z is the same as what we saw before. So the first time I heard about the reduce and fold operation was when I was listening to this podcast, LambdaCast. And on the podcast, they mention that it's called a number of different things in a number of different languages. So fold, reduce, accumulate is what we know it in C++11. Aggregate, I believe, is what C# calls it. Compress and inject. And so the point to know is that this reduce fold operation is a super, super common operation that is known as a different number of different things in different languages. And the second thing to note is that they have an episode called Morphisms where they talk a little bit about category theory. And this falls into the category of catamorphism, which is basically this idea of having a list or a foldable and shooping it down into one element. Now note that you can have a list of lists that shoops down to one list, so it doesn't necessarily need to be a single value. But it's this idea of taking a structure and then folding it down into a single value. It doesn't need to be the same value that the data structure contained initially, and we'll see that in a second. So taking a look at Rust, theirs is called fold, and it's very similar to accumulate and reduce. It takes a range and initial value. D has fold and reduce. And note that they actually have two different versions of each of these functions. They have one argument and a two argument. The two argument is similar to C++'s and Rust's. The one argument uses the initial value as the first element. So it doesn't take an initial value, it just uses the first element of the range as the initial value. Interesting to note. And when you start to pay attention to this, reduces are everywhere. We can implement many of the STL algorithms with a reduce. Stood count, counting the number of ones in our vector v. Taking a look at a sample implementation, this is not library quality, but you can do this and it works. Namespace template takes two iterators and your value that you want to count, captures the value in the capture list, two parameters. A is your accumulator, which keeps track of the running count, and B is your current element, and you just return A plus B equal to V. I know there's an implicit cast there, just ignore it. But when B is equal to your value, you end up adding 1 to sort of the running count. Taking a look at another example, any of. Returns true when the predicate that you pass it returns true for any of the elements in your data structure. So in this case, we have a predicate in the form of a lambda, which returns true if your element's equal to 3. Sample imitation of this. Namespace template takes two iterators. A predicate P captures the predicate when you make a call to reduce, initializing the value that you're going to return to false, because if you have any of a list that's empty, it's going to be false. And then in your lambda body, returning A, logical OR, the predicate evaluating B. And this is going to do exactly what any of does. So the point is that reduces are everywhere. This is not an exhaustive list, but I just went through. All of these could be implemented using a fold operation. Now note that the way that we implement accumulate and reduce, they sort of restrict the types that you can return. So you couldn't actually implement all of these with C++'s reduce or accumulate. The point is, though, that these are all catamorphic algorithms. These all fall into the catamorphism category of category theory. So just try and pay attention, and you'll start to notice. Ben?
So I did that as an exercise for my 2016 talk. Of the 90. I actually, as an exercise for a talk I did in 2016, implemented a bunch of algorithms as accumulate, as a fold, as Conor says. Of the 90 that were in C++14, 77 were doable as a fold.
So 77 of 90 algorithms that Ben Dean implemented could be implemented with a fold. So clearly I did not exhaustively go through here, but there's probably a lot more. So the point is folds and reduce are everywhere once you start to notice them. So there's a final note I want to make about reduce, and that's that they are parallel algorithms. They come with the ability to provide an execution policy, which will then turn your algorithm into a parallel algorithm. So I'm not going to talk about it here because I don't have time. This is a high-level talk. But if you're interested in this, there's a great article by Simon Brand, who works for Microsoft, called Stood Accumulate versus Reduce. The link's there. He talks about the three different policies, sec, par, and par unseek. And Bryce also has a great talk that you can go and watch. So these are resources if you want to know more. And note that accumulate and reduce, they're not identical. They are sort of reduces the newer version of accumulate, but there are differences in them. So accumulate's done, reduce is done, iota's done. We're now going to look at a problem, and it's going to be solvable with one of the 3 remaining pre-C++ algorithms. And I've taken this from a website and modified the problem a little bit. See if you can see the difference. So John Kalb is going to give Michael and Odin each 1 coin. John has n coins with different values. John wants the absolute difference between the value of the coins to be minimized so Michael and Odin don't fight with each other. Given an array of coin values, help John find this minimum. Now this is, may seem like a simple problem, but it's actually very important because we know that if Michael or Odin get a coin that's much greater than the other, this is what's going to end up happening. They're going to end up crying. So we really want to minimize this as much as possible. So here are a couple examples. If we have the coin values 1, 4, and 2, we want to give the coin values 1 and 2, because then the difference will be minimized to 1. And if we have the coin values 1, 3, and 3, this is the best case, because then Michael and Odin end up with coin values that are the same. So the difference will be 0. So does anyone know which of the 3 remaining pre-C++ 11 algorithms we can use to help solve this problem? Adjacent difference. So here we have a function, min value, that accepts a vector of integer coins. And then on the second line, we're declaring a vector of integers diff. We're going to shorten this. Coins will be C, diff will be D, just so it's easier to read. And on the first line, we sort. And then what we're going to do is we're going to call adjacent difference, which is going to calculate the differences between the adjacent elements. And that's a property of a sorted list that we know that the closest elements are always next to each other. So if we just take the differences, and then on the last line, take the minimum element from that list of differences, we're going to end up with the minimum difference. And note that we have to take the minimum difference from the second element in our vector D, because the way that adjacent difference works is the first element is always going to be the initial element subtracted or minus 0. So you're basically going to end up with the first element, which isn't a valid difference that we want to consider. Bryce?
Couldn't we do the last 2 in one pass, sort of a transform adjacent difference-ish?
So, thank you, Bryce. I'll pay you later. What's wrong with the second line? So implicit in Bryce's comment, so Bryce's comment was, can we do the last 2 lines sort of in one sort of transform reduce operation? And that's going to foreshadow a slide later. And the point is that we don't need to do a linear space allocation with vector D. If we look at the type signature, the function declaration, we're going from a list of integers to a single integer. Why does that require allocating extra space? We should just be able to get to our answer. And so a way to do that, not as elegantly probably as Bryce would like, but we'll get to that later, is by thinking catamorphically and using a reduce. Do not write code like this. This is bad code, and I'm pretty sure this code is actually broken. But this is just supposed to illustrate a point that you can solve this function or this problem without allocating linear space. So we do our sort, and we make a call to reduce, initialize it to the maximum value that an integer can assume. And then in the capture list, we initialize a value called previous, because we need to keep track of the previous element. And we initialize that to the first element. Then we have to have a modifying algorithm, or modifying lambda, because we're going to be mutating that previous. And then we calculate our difference, b minus previous, reset previous so that we can keep track of it for the next iteration, and then just return the minimum of our current minimum that we found so far, a, and the difference that we just calculated. So like I said, this is not good code you should be writing, but it illustrates a point. Vittorio?
Is reduce guaranteed to go from left to right?
No.
That's the whole idea.
So that is so this won't work. I said it's broken, and yes. So accumulate is guaranteed to go from left to right, and that is what's talked about in the resources that I provided. So there is a slight difference. You shouldn't be writing code like this where your lambdas are carrying state, because then it's not guaranteed to work. In a basic example like this, if you run this code, it actually probably will work, but as soon as you're doing stuff in production, it won't. So we're going to come back to that problem later, but for now, we're going to say adjacent difference check. So next problem is also going to be solvable by one of the 2 remaining C++, pre-C++ 11 algorithms. So you're given a length L of n posters, and the wall heights W at which they will be hung. They are hung at the 75% mark of the poster. Given Chandler has height h, how tall a ladder does he need? So what this looks like is we're given some inputs, and this represents 3 posters that are hanging on a wall. One of the points that we're given is the top of the poster, and the next list is going to represent the length of the poster. And so we're given the height of Chandler, who's right there, but unfortunately, he can't reach the posters. So we're going to need to give him a ladder, and this problem is asking us to find the height of the ladder, which is going to be here. So basically, the problem reduces down to what's the maximum point on each of these posters that's represented by where the green meets the orange, that is the 75% mark of the poster. So the way we can solve this is with a simple mathematical formula, which basically takes W, the top of the poster, subtracts the length divided by 4 because we're hanging it at the 75% mark, and then ceilings that because the problem states we can't pin it at or hang it at a non-integer value, and then subtracting Chandler's height from it. Note that if we do integer division with the L divided by 4, we can actually get rid of the ceiling because when you subtract something divided by 4, which we know is going to round down, and combine that, it's basically going to have the effect of a ceiling. So what does this solution look like? This is how I initially solved it. P stands for point, the point at which we're going to hang it. And unfortunately, I need the indexes in order to look into two different data structures. The list W and the list L. So the top of the posters and the length of the posters. If we only need one of these, we could just do this in an algorithm or some sort of range-based for loop. But because I need to look into both of these data structures, I'm not able to make use of those. So we look at Java, same thing. Except we're not using bracket operators, we're using get. And note that I consider this like an anti-pattern. Ben Dean actually talked about this a little bit in his talk last year, easy to use, hard to misuse. Whenever you see initializing a variable and then either modifying it in sort of if statements, you can use an immediately invoked lambda. The same thing here goes for when you're initializing a variable and then mutating it in a for loop, especially if it's p equals for every iteration. This is an anti-pattern. This is solvable some other way that's much cleaner. So let's go to Python. And this made me extremely sad. So Python has a function called zip, which basically takes two lists and gives you a list of tuples with each of the elements from those lists paired together. And then you can combine that with destructuring, similar to structure bindings in C++17, where it basically destructures each element out of your list of tuples now. So this gives us a generator expression, which we then can apply sort of a transform operation, your A minus B integer division 4, and then just fold it down using the max. And you can do that all in one line. So this is beautiful. Having this zip to combine two lists together and then at two at a time, stripping out those elements and performing a transform on it is just amazing. And it made me really, really sad that C++ didn't have this. And then Simon Brand tweeted. So I'm not going to go through this. The important part is the following. C++ code with zip in it. And so I tweeted at Simon. Oh my goodness. Ranges comes with zip? Please tell me this is coming in C++20. He said they are in ranges v3, but I don't think they're coming in 20. And I think the update is that it's still up in the air, but it doesn't look like it's going to get in because they don't have enough people working on it. And I responded, this makes me so incredibly happy. I was literally just Googling, does C++17, C++20 have zip? And Python, you're able to solve this so much more beautifully. And then 13 days later, this was December 3rd, 2018, 13 days later, I had just the most amazing weekend when I discovered inner product, which is a function that you should reach for when you want zip. It enables you to look into two data structures at a time and then perform a transform operation, binary operation, and a fold binary operation. So basically what this is doing, we're passing it begin and end of W, begin of L. We don't need to give it the end because we already have the length from W. And so it's just going to match the length that we're going from begin to end in W. We initialize it. And then our first lambda is our fold binary operation. Our second lambda is our transform binary operation. So A and B here are from W and L. They're two elements from W and L at the same time. We perform our transformation, A minus B divided by 4. And then in our first lambda, we perform our fold. So this was just fantastic. And funnily enough, there's some comments to be made about this. And I believe the next thing I'm going to show is some slides and a clip from Matt Galboat's talk. So for a moment, I'm going to plug Hannah's meetup, which is amazing. So she has a C++ meetup in Prague. She not only posts all the videos. Question? All right. Quote, the comment was, Vittorio does not find the previous slide very intuitive. Thank you, Vittorio. You agree with Matt. You'll see in a sec. And anyway, so Hannah's meetup, not only do they post all the talks to YouTube, they live stream them. Go follow her on Twitter. Go subscribe to this YouTube channel. This talk is one of the best C++ talks I've seen, and I don't think I've seen it anywhere else. So yeah, Kudos to Avast for investing in this kind of meetup and flying people out. Her talk lineup is amazing. I think you just tweeted your next speaker is going to be Eric Niebler, individual behind Ranges, who works for Facebook. Anyways, number of slides from Matt Gobelt's talk. I'm not going to go through them in detail, but it's very similar to what I did with the interview warm-up question. Oh, you wow, you guys are paying attention. Give him a chocolate, but this isn't my code. Holy smokes. We know who's paying attention. Anyway, so he points out that pre-C++ 11, this is disgusting, vector double : const iterator, and now we have auto. So that's fantastic, but we also have range-based for loop. And we also can solve this with an algorithm, with a function object. But now in C++ 11, we have lambdas, so we can solve it like this. And then someone told him, he actually didn't have this initially in his slides, but he added it, that you can solve this with inner product, where you pass, so this, I didn't even mention, sorry, this problem is RMS, root mean squared. You're squaring all of the elements in your vector of doubles, and then square rooting the sum of those squares. And someone pointed out that you can solve this with an inner product, just by passing the same range twice, which means you're going to be multiplying the elements together and then adding them up. So the default binary operations that you get with inner product are multiplies for the transform and plus for the reduce. But then Matt Galboat says the following about this.
And so this is a one line for the entire function that we had before. And I am not a functional person, so I don't personally prefer this style. I think it's more intention revealing to actually just see the code written out. But I know many people who I've worked with who are FP people, and they're like, yeah, this makes more sense to me. And with the ranges that are coming in C++ 20, a lot of this stuff will look even more easy to use.
So two important points there. One, Matt agrees with Vittorio and says that he doesn't find this intuitive. The second point is that this is going to get better with C++ 20 ranges, and that's going to be a recurring theme. So we come back to this solution. Yeah?
When you do numerics, that's not the best way of doing it, because you can overflow. Right?
OK, so there's a comment that says if we do it with numerics, it can overflow.
That's another way the absolute value of a complex number is calculated.
So yes, I guess that's a good point, but that's a detail. And right, don't miss the forest for the trees. So it's a good point. Pay attention, make sure that you're not overflowing. So the point here, though, is that inner product is not intention revealing. Inner product does not have anything to do with what we're doing right here. Not the best name. Transform reduce, C++ 17 algorithm. This is my favorite algorithm by far. Some people would still argue that it's not intuitive, but this is so much better than inner product in that it is explicitly saying what we're doing, and it's generic, transform reduce. So let's quickly take a look. Transform reduce, we're given two vectors, 1, 2, 3 for v, 2, 3, 4 for u, and the default operations that come with this are plus and multiply. So we're going to get 1 times 2 plus 2 times 3 plus 3 times 4 is going to be 20. But the point about this is that you can overload your binary operations. Do whatever you want. And transform reduce is still a good name for what you're doing, because it's a generic term for the fact that we're transforming and we're reducing. I had one problem with it, though. Why not call it zip reduce? Like, technically, there's a zip implicitly happening that we're not calling out, but we decide to call it transform, because there is a transform as well. There's both a zip, a transform, and a reduce. But I thought, why, inner product, it would have been so much better if the upgraded version was called zip reduce, because I think the zip is more important than the transform. We don't need to zip. So if we go to CPP reference, one sec, Michael, basically the third overload of this function only takes one range, and it takes a binary operation for our fold and a unary operation for our transform. So you don't need to zip. And that's why transform reduce is actually a much better name, because one of the overloads you're not zipping. So taking a look at what this looks like, if you have a vector v, 1, 2, 3, there's two different ways to code this, and I actually don't have a formed opinion on which way is better. So here we're basically summing the squared numbers. On the first line, we're just using reduce. And in the lambda body, we do both the reduce and the transform. The b times b is the square, and the plus to a is the reduce. And on the second line, we use transform reduce with the non-zipping version, where we explicitly separate the fold and the transform. So I would say whenever your fold and your transform operations get complicated, you definitely want to reach for transform reduce where you're not zipping. But in a simple example like this, I'm not actually sure which one's better. Michael, you had a question earlier.
I was just going to say, I think of zip as a packaging mechanism in order to deliver the data, as opposed to transform as an operation that's going to occur across multiple things.
That's a good point. So Michael pointed out that he thinks a zip is sort of a packaging mechanism and less of something that is going to be in an algorithm. Is that a good paraphrase?
Yeah, so we say transform reduce, I think of, well, there's two things occurring as opposed to zip reduce.
It's just a packaging and then one operation, and it ignores the more important second operation. Okay, yeah, so that's a good point. And then Michael points out that basically to ignore one of the main two operations happening in the algorithm probably wouldn't be a good idea. But it doesn't matter because I agree with transform reduce anymore. Or I agree that transform reduce is the name that this should have been. But yes, acknowledging both operations is important. Ben.
Transform reduce is analogous with regular transform, though, right? Because regular transform, the way we often use it is as a unary function on the
Yes.
range, but there's a binary version of it.
Yes, it's a fantastic point. And we're going to see more, hopefully, if I get to it later. But that is a fantastic point, that transform reduce is like an enhanced, or it's just functionality added to what we had in transform, which is a pre-C++ 11 algorithm. So if you want to talk, if you have a formed opinion or like use cases on which of these you think is better, come find me afterwards. I'd love to hear your opinions. But yeah, I don't have my mind made up about which is better here. So let's revisit our previous problem, the one where we were finding the minimum difference between coin values. So the last time we looked at it with a reduce, which I said don't code like this. And Bryce alluded to the solution that we're about to see. And that's the following. A transform reduce where the first range is the elements 0 to n-1, and the second range is the elements 1 to n. So basically, even though we're looking at two different ranges, they're both on the same range. We're just looking at different subranges, and that gives us adjacent elements. And then we can just take the absolute difference of the two elements that are adjacent to each other, and then the fold operation that we're doing is just taking the minimum. Anybody know a way we can improve this code, though? Yes, that's an improvement. Give him a chocolate. That's not the one I was thinking of. Anyone else? Oh yeah, that actually, yeah, give him a chocolate, but that's true. So that actually didn't work because you can't use a reverse iterator. This is not just returning a value, it's returning an iterator that needs to be paired as the same. So good point. There was one in the back. Yes, so that is half of the point. So the point to the back was we don't need the absolute a minus b. We always know b is greater than a because it's sorted. So we could just go b minus a. But even more so, we can just switch the ranges. Oh, so go ahead. Okay, yeah, so Ben and Vittorio, and then Odette at the back also get chocolates. Come and grab them later. So the first point was, yes, we don't need the absolute value. The second point was we don't even need the lambda. We can just make use of stud minus, and we just need to reverse the ranges. So that was something I didn't notice until months after I wrote this, but definitely neat. So this is the way to solve it in Haskell. I don't like formatting code like this. You can compose it like this. And this is something that's just going to come up, is that in functional languages, we don't need to have one algorithm that does it all. We can just compose smaller algorithms. So the way this works is it just sorts 1, 2, 4, takes the differences, and then takes the minimum. So digression. How much time do I have? 37 minutes? Yeah, we can watch it.
So let's see a simple example. We want to count all the repeated occurrences, consecutive repeats of a character. Usually, in functional programming languages, you would do this by pairing using the original array, then use its tail, and then you have pairs of letters. For each pair, you just calculate, check, are they the same, are they not the same, etc., and then you just need to sum everything. Conceptually, these are three completely different operations. Pairing with another collection, then iterating through all the elements and doing the transform, or as usually it's called in Haskell, map, and then you do the accumulation to count how many characters have been repeated. In C++, we have a completely obvious algorithm for doing this, which is called, completely as expected, inner product. So when you see the name inner product, this is immediately what comes to your mind, counting the adjacent occurrences of a character, right? Because inner and product is just that. So the inner product is a really cool example that you should never use, obviously, because this wouldn't fit the Phil Wadler quote. Now we do have the transform reduce, which sounds much nicer, and transform reduce could be fitted for this. But the problem is a little bit bigger than just the name. We have three different operations, but since we have the iterators and iterators are not easily composable, this couldn't have been just three different algorithms. This needs to be a single algorithm that is a composition of the previous three. So what can be done to remedy this?
So this was a talk clearly given from Ivan Kucic at ACC 2019. I actually watched this talk just like a week ago and added this to my slides. And I couldn't believe what I was seeing. I thought I was so clever that I'd come up with this sort of, 0 to n-1, 1 to n pairing using a transform with adjacent elements. And then he does the exact same thing and then gives a talk about it like 2 months before me, so he gets credit. But he says 3 really, really important things. So, I couldn't believe it when I saw this, but we need to unpack what he said. So one was that, inner product is a really cool example that you should never use. And if you watch my lightning talk on Monday, I already mentioned that. The second thing he said was transform reduce sounds much nicer, but that's not the whole problem. And the most important point that he makes, and I'm not going to read this whole thing, but the summary is that there's 3 operations happening here: a zip, a transform, and a reduce. But because iterators aren't composable, we need to pack those all into one algorithm. Whereas we want to be able to just have 3 smaller functions that we can compose together, which is what we saw in the Haskell solution. So this is going to be a theme. We've sort of heard a little bit of this before when Matt Galboat mentioned that C++ 20 ranges were coming. And if you want to hear what Ivan has to say about what he thinks is a solution to this, go watch his talk. So this is just a way you can solve this using the same adjacent difference algorithm we saw earlier in COUNTIF. So like I said, if you saw my lightning talk, we sort of showed this earlier. But note that we're making a call to one algorithm, adjacent difference, and then another algorithm, COUNTIF. Whereas in a functional language, we can just compose these. That's what the dot there on the last line is, a composition operator. They're 2 separate algorithms that we can call at once, and they get lazily evaluated. It's much nicer. And this is what ends up happening. We've got our values. It takes the differences between them and then just returns the number of times we see 0, which means the adjacent elements are equal. So that's the end of that digression. So transform reduce, it's amazing. Learn to love it. It's my favorite algorithm. And this is incorrect. So reduce should be here, but transform reduce should be up with inner product. So that was a mistake on John's slides. Fantastic talk, but definitely that was an oversight. And you should pay attention to, once again, the diagram of the plus being the fold operation and the multiplies being the transform operation that inner product and transform reduce come with. So now we've covered accumulate, adjacent difference, inner product, iota, transform reduce, and reduce. And that leaves us with one pre-C++ 11 algorithm, partial sum. So partial sum comes up way more than you'd think. And I'm not going to go through all the use cases. I'm just going to go through a couple, and probably what's my favorite problem in this whole talk. The first is range sum. When you have to have to sum multiple ranges. If you're going to do this once, it's just linear time. You just loop from 1 to whatever, call accumulate, and you're done. But if you've got multiple queries where you need to get the sum of different ranges, you can use partial sum, and I'll show how in a sec. Use with binary search. I'm not going to show an example with this, but there are many applications where you can use partial sum to construct a data structure of the partial sums, and then you use binary search to change a quadratic algorithm into an n log n algorithm. So maybe in the future I'll talk about that. And then you can use lambdas to overload the default plus binary operation that the algorithm comes with. So first, I've been talking about it, but I haven't even said what it does. If you're not familiar, partial sum basically is a transform that calculates the partial sums up to the given index that you're looking at. So given a vector of just all ones, the first element in your vector u, which we're going to be generating using partial sum, is going to be 1. Then the second is going to be the sum of the first 2 elements, which is 2. The third is going to be the sum of the first 3, which is 3, so on and so forth. For the second example, we have 1, 2, 3, 4, and you can see here we get 1 for the first element, 1 plus 2 for the second element, 1 plus 2 plus 3 for the third element, so on and so forth. Does everyone get that? I'm seeing nods. So the first example, when you have multiple queries where you need to sum multiple ranges, or a single range. So you can imagine we've got this map of key value, key value, which are both integers and queries. We've got our vector v, which is 1 to 100, and we need to sum up the ranges. So we want to know what's the sum from this index to that index. And like I said, if you just need to do this once, you just call and accumulate, you're done. If you need to do it multiple times, though, you can call partial sum, populate u with the partial sums, and then loop through, and you can get the sum of that sub-range by just subtracting the value at b from the value at a, or the value at a from the value at b. Does that make sense? I see nods. And this is a trick that I learned from competitive programming that happens very commonly. Whenever you have some problem where it has multiple queries where you have to sum these ranges, you can make most people don't call partial sum. They just write it with a hand-rolled for loop. But you can use partial sum and then do these queries. So that's a neat trick. Moving on to our next problem, which is probably my favorite problem in this whole talk. And I'm not going to say when or with which company, but I actually got this exact problem in an interview once. And I did not solve it as elegantly as I did now. I wish I had have. But yeah, given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it is able to trap after rating. So you can imagine if this is sort of like your mountainous range and then it rains, how much water is this range going to trap? So we're going to simplify this problem and look at an easier version, which involves the maximum being at the end. So you don't have sort of a mountain, you just have like an incline. And so the way you're going to solve this is you are going to basically do a single pass from left to right, keep track of what your maximum that you've seen so far is, and then at each step, add to some running sum the difference between the current height and the maximum you've seen so far. So it ends up looking like this. For your first one, your maximum is going to be 2. 2 minus 2 is 0. You don't add anything. From the next step, your height is 1. And so you subtract 1 from 2, which gives us 1. So then we know that at this point, we've got 1, I guess, unit of rain. 2 minus 2 is 0. We reset our maximum that we've seen so far to 4 at this point. And then on our next step, 4 minus 2 is 2. That gets us these 2. Next step, 4 minus 3 is 1. That gets us this unit of rain. Does that make sense to everyone? So it's a single pass, keeping track of the maximum height of your range that you've seen so far. And then you just do a difference of the current height that you're at. Whenever you're at the maximum, you just get 0. And whenever there's a difference, you're going to add that to your running sum. So what does this look like imperatively without using any algorithms? It's pretty straightforward. You've got your vector. You've got a variable m for the max that you've seen so far that you just initialized to be the first element of your range. Then you've got your answer, which is going to be the total amount of rain that you were able to capture. And then you have your range-based for loop. At each step, you reset your maximum. And then you also do a plus equals to the answer, which is your plus equaling the maximum you've seen so far plus the current element or the height that you're looking at. And then at the end, you just return your answer. Does that make sense to everyone? I'm seeing nods. There's a question at the back. Yeah? There's a problem with, so yes, this is a simplified version of the problem. You missed when I said we're guaranteed that the maximum is the last element. But you're correct, yes. If this was the original problem, it wouldn't account for the right side of our mountainous range. But this is how we would solve this imperatively. So how could we solve this with algorithms? Partial sum, overloading the binary operation with max. So we're no longer taking the partial sum at each point I. We're taking the max that we've seen so far at each index I. And so this partial sum applied to U basically gives us the white and blue combined. So we're going to get 2, 2, 2, 4, 4, 4, 5, 5, 5, and 7. Yep?
My intuition for this is like a reduce that remembers the previous things. Is that correct?
Yes. It could be this simple version of this problem could be solved with just a reduce as well. But we're trying to highlight partial sum right now. Yep?
Why don't you use this max and the false line?
Oh, great question. I tried to. So the question to be repeated is, how come I didn't use std max? Why do I have this in a lambda that wraps it? And that's because in C++, this actually worked pre-C++ 11. And then in C++ 11, we added an overload to max that takes an initializer list. So it can no longer figure out which max it wants, so we need to wrap it. But I actually have a file on my GitHub called useful function objects, where I provide this to you as a function object that you need. So I'm going to show that on the next slide. But so the point to make for the last call, transform reduce, we're then taking the difference of the white and blue and the white, which gives us the blue. Is basically what we're doing on the last line here. So there's another improvement that we can make on top of getting a nicer function for the max. Does anybody see what it was? It was similar to what we had before. On the last line, we know that the b is always going to be greater than the a. So once again, we can switch this to std minus. And over here, you see that this is UFO max. That's what I referred to as my useful function objects. Because yeah, it's irritating. Oh, whoops, getting mixed up here. It's irritating to see this when you should just be able to call max. So yeah, this looks pretty clean in my opinion. If only we had a std max that we could use. Unfortunately, we can't. But once again, partial sum. Partial sum, explicitly in the name, is that we're calculating partial sums. It's not partial max. It's partial sum. Not the best name. Introduce C++ 17's inclusive scan. Inclusive scan is your revamped partial sum. And you might be thinking, I see a few squints in the crowd. Is that the best name? This is, it's taken from other languages, I'm pretty sure. In Haskell, you have a scan function that does exactly this, a couple different versions. So this scan idea is, it's common in other languages. So yes, inclusive scan, but much better name. Let's go back to the original problem now. We were solving an easier version. How do we, so this is what Oded made a point at the back, is that this doesn't work for this side. We can't just do a single pass from left to right because at this point, max, 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 it's not going to work. So how can we modify the solution that we just looked at to solve the full problem? So let's take a look at our initial code. The first thing we need to do is to identify what? The maximum. So we've got the maximum now. The second thing we need to do is we want to stop our first inclusive scan, not at the end of our range, but at the maximum. So just replace that. Next after the it, because we want to include the maximum. Although I'm pretty sure actually at the maximum you're just going to end up subtracting 0, so you don't need the next. And so what's the second thing we need to do? Bendine with the solution. Inclusive scan with reverse iterators to the maximum. And you see this little reverse here. Where does that come from? It's a templatized type alias. So what's the main difference between typedef and using? Is that using is templatable. What? Using is readable. OK, two differences. Using is readable, and you can also templatize using. So this is C++ 17. It makes use of C++ 17 CTAD, class template argument deduction. If you're using C++ 14, with the reverse right here, you need to use a decal type on the iterator to get the type. But yeah, C++ 17. Pardon? OK, and so there's a comment from the front that said there's a make reverse function, so maybe you don't even need to do this templatizing using and then casting. But yeah, didn't have to make too many changes, and then we solved the problem. Ben?
Does inclusive scan return the iterator, in which case you could use it in the second inclusive scan in place of beginning?
Oh, great point. Great point. So Ben Dean with a fantastic comment that there is, from inclusive scan, it returns an iterator that we could use in the second one, and we wouldn't actually have to use reverse iterate. You would still need to reverse it, but right. You'd still have to reverse it, but the point is, well, so you could make use of the iterator that is returned from the first call to inclusive scan, is the point. Yeah. So yeah, this is probably one of my favorite pieces of sort of competitive coding algorithm. It makes use of 3 different algorithms: max element, inclusive scan, and transform reduce. And it makes use of all these function objects, plus, minus, UFO max, and it's super clean. And if you look at the imperative version of this, you're basically adding a second for loop to what we had before, looping backwards. Ben has another comment, maybe?
Yeah. So with the output iterator, you could...
You definitely have to go right to left.
You can size your vector of use by the max of where the max element is, basically. You only need, like, if the max element's in the middle, you only need half the range, because you can do the inclusive scan and the transform reduce, and then the inclusive scan and transform reduce at the second.
Yeah, I think that's right. So the Ben's comment, or you had the mic, but that basically we don't need as much memory. You'd still need to know like where the max is, like, because it might not be at the center. But the point is, but you need to know the distance. Yeah, exactly. The bigger half is the point. And so the point is that you don't need as much memory. Like, this is suboptimal in terms of the extra memory that we've allocated, in that whatever is the larger half where the maximum occurs, you could only allocate that much and just sort of reuse. Yeah. So yes, there technically, I'm sure, is a solution where we allocate 0 memory, but then it wouldn't be as nice for demonstrating inclusive scan. So, but it's a good point.
But maybe there is a version in which I don't know, the function that you pass to inclusive scan has a side effect that can keep track of things while it's doing this inclusive scan.
Yeah, possible. It's possible. So yeah, to paraphrase, there could be a couple other ways that are more efficient to solve this. So we've covered accumulate, adjacent difference, exclusive scan, inclusive scan, inner product. Or I guess technically we didn't include exclusive scan, but basically the difference is you provide an initial value and it doesn't take the initial element is the initial value, and then it excludes the current element that you're looking at. But it's basically just a variation of inclusive scan. So if you understand inclusive scan, it's just one step to understanding exclusive scan. Inner product, iota, partial sum reduce, and transform reduce. We're going to ignore the other two, and we're going to move on to probably what is the most important part of this talk. And it's the algorithm intuition table. Yeah. Damn it. I made this slide. I made these slides last night. See, I apologize. Hope it's going to be spelt wrong on the next slide too. So here's a table of most of the algorithms that we've looked at so far. Iota really shouldn't be there, but I just felt bad leaving it out. Poor iota. And these are 3 properties for all of these algorithms. So the first property is the number of indexes we're viewing at a time. Note that it's not the number of elements. So if we're looking at transform that takes 2 ranges, I consider that 1 index because it's a single index across 2 different ranges. 2 indexes means we're looking at index I and index I plus 1. The second is an accumulator. So accumulator is what typically we call the first parameter in a binary operation that we're passing to a fold or reduce operation. It's the value that's being dragged along and plus equal to, or whatever the operation that you're doing. That's what they refer to it in functional programming. You don't hear it as often in C++, but the first parameter of a binary operation that you pass to a fold or a reduce is referred to as the accumulator parameter. And okay, so apparently I have not read the wording. Remember I said I'm just a dude, not an expert, but it is actually what's used in the wording. And then the second is whether the algorithm is a reduce or a transform. Note, this is just sort of a category. I hope I'm not reinventing category theory here, but the idea is that accumulate, inner product, reduce, transform, reduce, these are all reduce algorithms, whereas partial sum, exclusive scan, inclusive scan, these are all transforming or mapping. They're creating a new range. This is a way to think about it. So 3 properties, and you can see 3 properties. They're each binary. We should have 8 algorithms, 2 to the 3. We've only got a few here. So adjacent difference, just for example, it takes a look at 2 indexes. It doesn't have an accumulator. It's only looking at each index at a time. And then at the end, it's generating sort of a range. So it's transforming. It's not reducing. So the first thing we're going to do is we're going to add adjacent reduce. We've seen this example a couple times where we're basically taking a look at the adjacent elements, and we're performing both a transform and a reduce. This is just basically a specialized form of transform reduce, but it's common enough that I want to throw it up here. And note that the asterisk next to this 1 means that we can look at multiple ranges at a time. So even though there's a 1 here, the 1 could apply to 1 range, or it could apply to 2 ranges. Not so much for inner product, but for transform reduce, we do have that ability. Vittorio. What does? Well, first, adjacent reduce is a specialization of transform reduce, not reduce. Because reduce can only look at 1 range. Transform reduce can look at 2 ranges. So basically, adjacent reduce, it is just a transform reduce. I'm using inner product here, but it could, pardon? Nope. Yes, on a single range, but you're passing it the 0 to n minus 1 and the 1 to n. So that's what this f, so maybe I went over that a bit quickly. The f and then decrementing the exactly. So it's just, I wish we had this in the algorithm because it seems to come up so often. And as mentioned, I was talking with Bean the other night, and he pointed out that, yeah, this is a common pattern in functional programming. It's called zip tail. You zip with the tail, which is the 1 to n of your range, and then you perform operations on the pairs. So another spelling mistake, solving a problem with the algorithm intuition table. So here's our problem. We're not going to read it. It boils down to this. Given a string of 1s and 0s, return true if the longest contiguous substring of equal elements is greater than or equal to 7. So 2 examples. Our first example, we have 2 zeros, 1, 2 zeros, 1. There's no substring that has equal elements greater than or equal to 7. But on the second one, we've got a bunch of zeros in a row that has more than 7. So how would we go about solving this problem? Imperatively, this is what it looks like. So max players, we're going to shorten to MP. Current players, What? Yeah, that's it. I'm too focused, but yes, that is the Westconst. Vittorio and Bean both get another chocolate. Yeah, I'll just give this. You guys have been answering so many. You can have this afterwards. But yeah, we're going to shorten max players and current players to MP and CP in a second. And basically what we're doing here is max players is going to be our final result, and current players is the current number of equal elements that we've seen in a row. And then we go through our indexed for loop, starting at 1. We're checking, are the two elements equal to each other? So SI, is it equal to SI minus 1? If so, do an increment on our current players. Otherwise, reset it back to 1. And then once we've done that, we just set our max players equal to the maximum that we've seen so far, and our current, ooh, that's a bug right there. That temp should be current players. It's the same thing. A pre-increment or a post-increment is the same as a +1. Okay, yeah. So the point is that I shouldn't be using a pre-increment or a post-increment. I should just be doing +1. Right, right. I changed this line. I used to have it differently using the ternary operator to mimic something, but I didn't like it, so I changed it last night. Anyways, it's a good point. And then at the end, you just return is our max players greater than 7. So this is imperatively how you'd solve it. So if we go to our algorithm intuition table, how do we choose our algorithm? Well, first, how many indexes do we need? We're looking at 2 elements that are side by side. So that's 2 indexes. Do we need an accumulator? Well, yes, because we need to calculate what's the current number of equal elements that we've seen in a row. And at the end of the day, what are we returning? A single element, or are we generating a range? And it's that we're doing a reduce. So we choose adjacent reduce. So here's our solution. And this makes use of a functional programming trick where when you need both sort of a temporary and then a maximum of the temporaries that you saw, you use a pair. So we're calling adjacent reduce, initializing our pair to be 1, 1. And then our pair is our accumulator. And on the first line of our lambda body, we're destructuring our pair to be the max player and the current player. So like I said before, max player is MP, current player is CP. So this is a little bit easier to read. So the max player is the first element in our pair that we're using as our accumulator. And the second is our current player. And we're basically doing the same thing then. So our second is going to be an equal, which we get by using the equal to function object. So that's going to be our transform that we perform first on the adjacent pairs of elements in this adjacent reduce algorithm. So it's going to look at the adjacent elements, look are they equal, and transform those into a Boolean. And then we're going to pass that with our accumulator to our fold lambda that then basically does what the imperative solution does. So if the elements were equal, we do a pre-increment, as Oded pointed out, that we should be doing +1 there. Otherwise, resetting to 1, and then returning a make pair of the maximum. Question?
Are you scanning the whole string when you only need to go, when you hit the first 7, you should bang out?
Yes, that's a great point. So this algorithm does not short circuit. It could be performed more optimally by returning out. Yes. So this is an adjacent reduce that is a specialization of transform reduce that takes 2 binary operations, the fold, which is this big lambda, and then the transform, which is the stood equal to. So the transform on the last line is applied first and takes our adjacent elements and converts them to a vector of Booleans. Question?
Following up on the comment from the back about short-circuiting, so I don't see a way you could do this with an algorithm like the reduce you're showing here.
You can't.
So is this like a win for imperative programming?
Maybe. But yes, it's a point to be aware of, that sometimes you want short-circuiting algorithms. And we're going to see in a second that there are short-circuiting algorithms built into the STL algorithm library. Another question?
So I'm pretty sure it will not work, but there is a break here. Inside, it will not apply to the loop in which this algorithm is.
No. Yeah, so the question was, can you use a break inside an algorithm? The answer is no. So, pardon? Ben Dean's comment, you could throw an exception. Probably not what you want to do, though.
But if you need to short circuit, that's the only way. I mean, to make it more efficient.
Yeah. So the point is, yes, you can create a short-circuiting version of this that'll be more efficient. The point here is that functionally we can solve this way better. We have a number of different algorithms that we can compose. And what this is doing is group is a function that's a little hard to see up there. But it groups a list into sublists, or in this case, a string into substrings, a list of substrings of equal elements. And then we can just take the length of those substrings, 2, 1, 2, 2, 1, or 2, 1, 2, 1, and then take the maximum of those, and then just check is that greater than or equal to 7. So functional programming for the win. So back to this table. Let's extend it. We have 3 properties that are binary, and we're only looking at how many different versions. So the first 2 are 1 yes reduce, 1 yes transform are the next 2, so that's only 2 out of 8. Then we have 2 no transform, which is another one, and 2 yes reduce. So we've only got 4 out of 8 algorithms here when we should be able to complete this to have a set of 8. So anybody know what algorithm matches this? Looks at 2 at a time, doesn't have an accumulator, and reduces. No. We want to replace the happy face with an algorithm. That's a great question. That's why there's an asterisk next to reduce, because it is a reduce, but it's a short-circuiting reduce, which could be implemented in terms of a reduce which doesn't short-circuit, but the way that it's implemented, it short-circuits. Pardon? Who said it? Adjacent find. So there's a reason that I have an asterisk. You can see it next to the reduce. It's reduce asterisk. It's a short-circuiting reduce. You could implement adjacent find in terms of reduce, but it's really not. You've got a while loop. As soon as your predicate returns true, which in this case we're trying to find 2 equal adjacent elements, you're done and it returns it. But it's still, you can think of it as a reduce. Next up. 1 asterisk, no transform. This one should be easy. Who said it? Transform. So this is a well-named function, unlike some of the others, which we'll get to in a sec. What about this one? 1, no, and reduce. Oh, dead set at the back. It's fine. Once again, with an asterisk, because it short circuits. It's not actually going to fold over the whole data structure. It's going to return as soon as the predicate that you pass it returns true. Who's seen this example before? Wow. 2 people. And it's amazing that I happened to be talking to Ben, one of the individuals that raised his hand in the crowd, about this example. So you can generate a Fibonacci sequence with transform that basically passes for the 2 ranges, one that starts at the beginning and one that starts at the second element, and then outputs to the third element. And then the binary operation that you're performing is just a plus, which you've initialized your vector using this constructor here, all to 1. So initially your vector is all 1s. And so when you add 1, 1 together, you get 2. And then for your next iteration, you add 1, 2, and you get 3. And now you're generating Fibonacci. And when I talked to Ben, and this is amazing, so this is why C++ now is so awesome, is that I didn't have the next slide in my slide deck initially. He pointed out that you can solve this with a more specialized version of transform, which I'm pretty sure is what Oded was going to say. Nope. Yes. So you'll be fine. So the question was, will this perform in order? Because otherwise you're going to end up overwriting yourself. Yes, it will. But the point that Ben made is, and he actually brought this up. I can't remember what I was talking about. And then Ben, oh, have you seen the example where you can use adjacent difference to calculate Fibonacci? Because adjacent difference is basically just a specialized version of transform, which upsets me. Why did they call it adjacent difference? The default operation that adjacent difference comes with is minus. But here, we're overloading it to plus, or replacing it with plus, and now it has nothing to do with difference. Adjacent difference should be called adjacent transform. And that's how you should think of it. And it really upsets me because it's such a great algorithm. It's a specialization of transform when you pass 2 ranges to transform. But you're never going to think of that because it's called adjacent difference. You're only going to think about it when you want to take the difference between 2 elements.
What would be your default or no default?
Aha. Thank you. The question was, what would your default be? The next slide. talks about the default operations that come with your algorithms. I would argue none of these algorithms should come with default operations. That's the way functional programming works. You're given generic algorithms that don't come with default binary operations, and you specify them. That's why in the Haskell solution, we saw map adjacent. That is basically just adjacent transform. In Haskell, they don't have transform, they have map. They're the exact same thing, and their algorithm is called map adjacent. Ours should be called adjacent transform. And Ben has a comment.
Do you think
Give him the mic.
in Haskell, its default operation is, well, we would call it make pair. Right. So it's actually zip, right?
Well, yes, zip tail.
No, but zipping together two sequences, making pairs of the pointwise.
Yeah, so maybe there could be a zip in there. So the comment was, yeah, basically that maybe there should be zip in the name. But the point is, regardless whether you're putting zip in or whether you're putting transform in, adjacent difference is not what this algorithm should be named. And probably, if I had to guess, make an educated guess about back in the 90s when Stepanov was creating these, or whoever ended up initially creating this algorithm, it was that the use case was commonly like that, way more common that you needed to subtract adjacent elements than you needed to add them. And so they said, oh, well, we want to make it easier for people to use these algorithms, so let's give it a default, and then if they want to, they can override it, but we want to make this more approachable. And that is something about functional programming. There is a little bit more of a learning curve in terms of higher order functions and passing binary operations and whatnot. But I would argue that adjacent difference shouldn't have the name. Bryce.
The other annoying thing I find is that there's only we don't have sufficient already overloads of transport. There's one for 2 sequences.
Yes.
One sequence.
But that's it. Exactly. So Bryce's comment was that we only have overloads for 1 range and 2 ranges. What about 3, 4, 5, 6?
Well,
Yeah. So hopefully with C++20. Ben?
So the other slightly annoying thing, and it doesn't matter in practice, and I can't remember now which of the algorithms specify it, but some of them, and probably transform is one of them, specify that you can't change your input ranges. And if you're zipping with your tail, like in the Fibonacci version, then you're writing to your, effectively you're writing to your input range, I think.
Mm-hmm.
So technically undefined behavior because you're violating the function's conditions, but it's annoying.
Yeah, that's a good point. Anyways, it says 4 minutes left. I might go a little bit over, but I've only got like 18 slides left. So the next point I'm going to make is the following. Oh, wait, I'm not going to make a point. So quickly, I'm going to go through this. We're missing 1. So if you look at it, we've got 7 out of 8 now, but we're missing 2 yes transform. And so I figured, okay, I'll quickly go implement this, sad face, because we don't have it. And I'll call it adjacent inclusive scan because, why not? That's basically what we're doing. We're just doing an inclusive scan, but looking at 2 elements at a time. So that's why we've got the 2 indexes. And I went and looked at the Microsoft's, because that's what I have, Visual Studio on my computer. I quickly put it together. You see previous element, accumulator. We're not going to really look at it. And this is a use case of how you would do it. Basically, this is doing partial sum, but only including elements that are equal to each other, adjacently equal to each other. Otherwise, you're not including it in the partial sum. But does anybody know what's odd about this or what I just did accidentally? That's a good point, but not what I'm looking for. The point here is that we already have this. These were the 2 that I ignored. I realized this 2 days ago. So yeah, well done to the people that behind adding these algorithms. They completed the set of the 3 different properties: transform, exclusive scan, and transform inclusive scan. So where I had adjacent inclusive scan is what we wanted with transform inclusive scan. So yeah, pay attention to the default operations. The next point is just to echo what Ivan Kucic said and Matt Goblet said. It's not composable. How many of you know of find if as an algorithm? It's basically find with a filter. But what if we wanted to add if to all of these? Well, now we've got 4 properties. 2 to the 4 is 16. And you can think of those runes that were on Jonathan Bakar's slides as all different sort of, there's underscore n. And the point here is that these algorithms are not composable. And I think C++20 ranges is really going to help with that. So one last problem You might have noticed at the beginning of my talk, my title slide, I had the following. Who knows what this is from? Or like what this represents? Scrabble. It's a board game. Anyone not familiar with Scrabble? Okay, so Scrabble is basically a word game where you've got this board that has double letters, triple words, and then each of your tiles has a value. And you spell words in sort of a crossword-like fashion and try to score points by superimposing the value of your letters on this board. So you spell the word algorithm, you place it here, you need to calculate the score. What algorithm is this? Or transform reduce. They're everywhere. Once you start to learn your algorithms, you find them everywhere. Technically, you might be thinking, oh, well, you avoided the fact that you could have a double word, and then double word changes the algorithm. Yes, I know. But it's supposed to be an illustrative example of just these algorithms are everywhere. Like, I never used to see them, and now that I know them, I see reduces everywhere, and I see transform reduces everywhere. So that's the point I want to make, is that Scrabble is like one of my favorite board games, and now when I think it, I'm sort of doing a transform reduce here. And before we conclude, there's a bunch of small points I want to make. It says I got 10 seconds, although we started late. A bunch of other conferences. Every single one of these conferences has a YouTube channel that posts all their talks. So thank you to both John and Danny and the video crew. This is my first conference that I've attended, but I've been able to watch just hundreds and hundreds of videos online because they all post them online. Also, podcasts. There's 2 C++ podcasts. I think most people are familiar. Jason and Rob are for CPPcast, and John Kalb, the organizer of this conference, and Phil Nash are for CPP Chat. And there's also 2 functional program or podcasts that I highly recommend. I think raise of hands who's read these. Oh, it's actually less than I think, 80%. So this is more for the YouTube audience, but if you're going to be C++ Pro, you should definitely go read Scott Meyer's books. Subscribe to me on YouTube. I have a channel that solves competitive programming channels, and I post things to Twitter as well. If you're interested in any of the slides from my talks or the videos from my talk, go to this link here. Every single code slide has a different file with the right extension, so it's syntax highlighted correctly. This isn't updated because I was changing slides up until yesterday, but by the end of today, it'll all be updated. And to conclude, algorithms are awesome and they're fun. Especially transform reduce, but we covered a number of other ones. Know the default operations that the algorithms come with, but then leverage them with function objects and lambdas. And know that C++ 20 ranges are coming, where hopefully we're going to get composable algorithms. Thanks. So there's one more thing I'll say. This is my first time giving a talk, so more probably than others, I would love feedback. So here's the link you can go to. And yeah, questions? You want to throw?
For the example of the RMS, can we in 10 seconds implement a better version that is more accurate for doubles functionally?
Sorry, so for the RMS example,
yes.
Can we what?
Implement a more accurate version of it with your style. Do you imagine how to? I mean, the typical way is to find the maximum first, the maximum element in absolute value, and scale all the elements through that as you sum the squares.
My guess is there probably is. Or sorry, Ben, do you want to respond?
Yeah, I'm wondering if you would do that.
You can throw the mic to Ben.
You can use a balanced reduction algorithm. The standard library doesn't provide any, but it's well known in the literature to provide more stable and less loss of precision.
So balanced reduction, less loss of precision for the RMS example that was in Matt Godbold's slides. Other questions? No? All right, thanks guys.
Good job.